All right, so in this video we'll finish what we were doing in section 2.2. So first thing we're going to look at is dot plots. It says here a dot plot is made by placing a dot for each observation horizontally in increasing order and placing a dot above the observation each time it's observed. So here you can see these are minutes to eat breakfast ranging from 0 minutes to 12 minutes. So some people didn't have breakfast. There's 1, 2, 3, 4, 5, 6. So we have 6 observations of 0. You could count up all your dots and that would tell you the total number of people that you observed. And it's just another way to picture or make a picture of your data. Kind of like the distributions that we looked at before, the discrete ones. Instead of using bars, we're using dots here. So let's go to the next slide. And you can see we talked earlier with some discrete data about people arriving at Wendy's during lunchtime in 15-minute intervals. And anyway, so you could put that data into a dot plot. Now, if you do that in StatCrunch, you just hit graph, dot plot, and then var1. I think there's one homework problem where you're going to want to import your data, and then these are the menu items that you choose. The other thing I would just say is if you have any problems, just watch the video that's by the author. Again, it's very good. Let's go ahead and move on to a discussion of the shape of a distribution. So you can look at the distribution of the data here. Notice here you're probably under 50 observations, I should say, yeah, under 50 observations here between 0 and 10. And from 10 to 20, you've got almost 300 observations or somewhere right around there, and you can just go from there. But the main thing is this is symmetric, so this would be like your line of symmetry, and you can see some symmetry there, and it's also bell-shaped. And so this is what we mean when we talk about the shape of a distribution. You can see most of our data occurs in the middle here. Let's go ahead and move on to discuss the 4 different distributions that we want to be familiar with. So figure A is a uniform distribution because the frequency of each value of the variable is evenly spread out across the values of the variable. So for example, if you were to roll a 6-sided die 100 times, you would expect to get as many 1s as you get of 6s, and the same thing for all the numbers from 1 to 6. That's because you have a 1 in 6 chance of getting each of those outputs. Another example would be wait times for a bus. Let's assume that a bus comes exactly every 15 minutes. So you know how it is. You get there, you're hoping the bus is about to show up. Hopefully the bus didn't just pull away, or you're looking at a full 15 minutes. But it's as likely that you're going to wait there 6 minutes as you are going to wait there 15 minutes. So that would have a distribution that's uniform. We talked about the bell-shaped distribution. Again, you can see the symmetry, and you have what we call tails on each side. The types of data that tends to have this kind of distribution would be if you collected like the weights of men, or the heights of men, the shoe size of men. For example, in the United States, we could look at SAT scores of college students in a given year. So these are the kinds of things where you're going to have, you know, most people are going to be in the middle, and then you have your low scores and your high scores, and it tends to have that bell shape. A lot of data has that kind of shape, that kind of a distribution. All right, there's 2 more here. So the distribution in figure C is skewed right, Notice that the tail to the right of the peak is longer than the tail to the left of the peak. So I don't really think of these as much as tails as I should say I just look at the longer tail and I think of that as the tail, but these are both considered tails, but you can certainly see that the tail on the right is longer, and so this is skewed to the right. Here you're skewed to the left because the tail on the left is longer. So some examples of data that work that way, that are skewed right, would be like the number of children in U.S. households. Now, this is not uh, a distribution for that, but basically you would have, 0 to 3 children. You'd have a whole bunch of people in that area. And then as the number of children gets bigger, like 5, 6, 10, 12, you're going to have, it's going to tail off. And the long tail is going to be on this side. U.S. annual household income, same type of thing. Most people are going to be somewhere in the kind of the average range, and then as people get richer and richer or have more income, it's going to tail off. Now, it turns out you have a bunch of multimillionaires. I guess that's probably has a lot to do with, well, there's a lot of things, but certainly the internet has made a lot of millionaires and billionaires, but it does have that kind of a tail to the right. Most of the people are going to be on the left here, and the tail on the left will be very small. Skewed to the left, these kind of distributions tend to be or affect the elderly. Like, for example, ages of hearing aid patients, well, most of them are going to be older, and you can see that there's going to be a lot fewer here, especially for really young people, and it's going to slowly grow, but again, most of your data will be here, so your tail is to the left. So that's just one example. Let's go ahead and look at a couple of things here. When it comes to qualitative data, we don't talk in terms of the distribution of the data as far as its shape. It's important to recognize that data will not always exhibit behavior that perfectly matches any of the shapes given in the previous figures. To identify the shape of a distribution, some flexibility is required. It's not always obvious that it's one of these four, and I would say it's debatable sometimes, and that's what they're saying here. People may disagree on the shape, since certainly identifying shape is subjective. All right, let's move on to the next slide. So here's an example. The figure displays the histogram obtained in a previous example for the fine paid for parking and camera violations in New York City. Describe the shape of the distribution. Well, you can see it's kind of bell-shaped. But the problem is it's certainly missing that bell shape in that area there, even over here a little bit. And so it's not really bell-shaped, kind of has some of that shape, but we wouldn't say it's bell-shaped because it's not symmetric, although it's not a symmetric bell-shaped curve, but there is some symmetry going on here. You can see here and here and here and here, maybe even here and here, but that's about all you could say about that one. Let's go ahead and move on to stem and leaf plots. This is actually a 2.3 topic, but we threw it in here because we wanted you guys to see this one. There's others in 2.3 that we won't discuss much. We talked just a little bit about a line graph, but there's some others there as well, but we don't cover that section other than the stem and leaf plot. And so a stem and leaf plot is another way to represent quantitative data graphically. You will form a stem and then a leaf for each data point. So you have a stem and you have your leaf. And so what does the raw data look like here? So basically the 4 is the tens place and this 1 is in the ones place. So this represents 41. And then here you have 52, 57, 58, and then we move on to the 6, we have 65 and 66 and so on. By the way, you can see that if you were to turn this upside or to the right, or rotate to the left, I guess, it's got that bell shape a little bit. Let's go ahead and move on to the next slide. So here's an example of how we might, or how we would put together the stem and the leaf. Basically, the leaf is just the last digit. So here the stem would be 18, and 3 is the leaf. For 25, 2 would be the stem, and 5 would be the leaf. In your homework, you'll have one with decimals. So you might have 1.3. So the 1 would be the stem, and the decimal part would be the leaf. And something in the problem would indicate, basically the data would indicate that your stem is a decimal. All right, so let's actually make a stem and leaf plot. Now, for this data, it's going to be pretty nice because it's already been ordered. If it wasn't ordered, you would want to order it. And so basically, our stem is going to be the tens place, and our ones place is going to be the leaf part. So we'll start with 1 and 5, and we also have 16, so we'll put a 6 here. So this represents the numbers 15 and 16. And then we have 21, 2 23s, and 2 26s, so let's put a 2 here. We've got a 1, 3, 3, and 6 and 6. And so that takes care of these guys. Then we have 2 30s, or I should say 2 that are in the 30s. We have 30, so we'll write that 0 there, so this represents 30, and also 32. And then 41, we put the 4 here and the 1 there. All right, so that's how you would draw one of those. Again, you can see this one's kind of bell-shaped. Just look at a couple more examples of distributions. So here's another stem and leaf graph, and if you turn it this way, you can see that it kind of has a tail to the left, although it's not really much of a tail, I would say, but it does have a tail to the left, so it's skewed left. Some people might argue that. I mean, most of the data is kind of all around here, but you definitely have the most here and here. So it does seem to have a little bit of a tail. So I would say that's skewed left. And this one is also skewed left. You can see that right here. Even though there's just one of each of these, we definitely have a distribution that's skewed left. All right, that's actually the end of this video. I don't have any more to say about section 2.2.